Let's continue talking about solubility. 17.4, solubility equilibria. And this is continued. So we've already started section 17.4 in a previous video, and we're just picking up and carrying on. So let me just remind you briefly what we're talking about. We're talking about having like a beaker, and we're going to put some water inside that beaker. And we're also going to put inside the beaker a chunk of a substance such as AgCl, silver chloride, a substance that is not soluble in water according to our solubility rules, which we now know means that it is just barely soluble in water. It is kind of a tiny bit soluble, but not hardly much at all. So a little bit of the chloride ion and a little bit of the silver ion will dissociate and dissolve. So a very small amount of this solid silver chloride will dissolve in solution. And in this section, we're really concerning ourselves with questions like how much silver or how much chloride, what is the concentration of those ions that are up in solution. So one of the key things with the solubility equilibria problems has to do with the concept of saturation, or a solution being saturated. When a solution, like one of these solutions, is saturated, that just simply means that it is in equilibrium. It has reached that perfect amount of silver ion and chloride ion that have dissociated and gone up into the water, and the balance between the silver ion and the chloride ion and the solid AgCl is just perfect. And when it is in equilibrium, the solubility constant, the Ksp, is going to be equal to the concentration of, for this example, the silver ions times the chloride ions. And of course, you know that this equilibrium expression is going to change depending on what solid substance we're dealing with. And if the solution is unsaturated, that means that it has less than the desired amount of dissolved ions. So because it's not perfect, it's not in equilibrium. Because it's not in equilibrium, we can't calculate a Ksp. We can only calculate Ksp if we know that the solution is in equilibrium. So instead of calculating a Ksp, we calculate a Q, which is just a placeholder for Ksp. It's a symbol that lets us communicate that, hey, this system is not actually in equilibrium yet, but it's working on it. And when the solution is unsaturated, it's not in equilibrium because it's unsaturated. These concentrations of these ions are going to be too small because it's not saturated, it's unsaturated. If those numbers are too small, the value of Q is also going to be less than the value of Ksp, which would be representation of the perfect amounts of dissolved ions. And then last but not least, if we have a supersaturated solution, this is where we have too much dissolved. Too much has been dissociated. So it is also not in equilibrium because it's not representing that perfect balance. And because it's not in equilibrium, again, we cannot calculate a KSP. We have to use the letter Q because we have to communicate this system is not in equilibrium. And this time, not in equilibrium because we're supersaturated. That means that our silver and chloride concentrations are too high, which means that Q will be too big. It's going to be greater than our KSP. So that's just kind of a summary of what we did in the last video. So what we're going to be doing from here on out is actually numerically calculating the solubility of solutions that are in equilibrium and therefore saturated. In equilibrium, which also means that the solution is saturated. We have two different ways of expressing how much substance has actually dissolved and dissociated. One way that we can express this is the solubility. The solubility is defined as the grams of the solute, the substance that is the solid, that has actually dissolved. So not how much did we put in the beaker, but how much of it actually dissolved. And this is going to be divided by the liters of our solution. The other way that we can express this is called molar solubility. The molar solubility calculated almost the exact same way. This is the moles of solute. Again, the solid that has dissolved. And we are dividing that again by the liters of solution. So let's learn how to do some of these calculations. Let's start with an example. What is the molar solubility of PbF2? And in order to solve all of these problems, we need to know the equilibrium constant, the KSP. For PbF2, KSP is 4.1 times 10 to the minus 8. So the first thing that we're going to do is write a balanced chemical reaction that's going to help us get an idea of what's happening when this substance is dissolving and dissociating. We are starting with lead 2 fluoride, which is a solid, and it is in equilibrium dissociating to the lead 2 ion, Pb2+, and also 2 fluoride ions, F-, both of them are aqueous. Pay attention to your stoichiometry. The formula for PbF2 has got that 2 in it, which means that we need to have 2 fluoride ions in the product out here. So the solubility or molar solubility is going to be a term that's represented in the ICE table. The molar solubility, let's think about what it's asking us here. It's asking specifically, molar solubility means how many moles per liter of PbF2 dissolve. Or you could also think about it as dissociate, because it does split apart when it dissolves. Or you could also think about it as react. You could think about this in terms of a reaction. So how many moles are going to dissolve or dissociate or react, not reaction? Any one of those questions, basically asking the same thing. And that answer, the answer to that question, is going to be found right here on the ICE table. What is the change for PbF2? How much PbF2 is actually going to be reacting. So we have to fill this ice table out in order to be able to answer the question, because the answer is in the ice table. Now, filling this ice table out, we do not have any idea at all about how much PbF2 we're starting with. It's a mystery. We have no idea. It's not an X type of a mystery. This is a mystery that we're not going to be able to solve. We don't know what the amount of solid is in this solution, and you're going to quickly find out that it doesn't matter. Before the reaction starts, nothing has happened, so we have no ions present at all in the solution. Once this reaction starts, we are going to lose a certain amount. We're going to see a certain amount of PbF2 dissociating, which we're going to call minus X, just like normal. And then because of the stoichiometry of this reaction, we're going to have plus X and plus 2X. Where does that 2 come from? Comes from the molecular formula, the stoichiometry of the F minus, the 2X. It's right there. So when this reaches equilibrium, we still have no idea how much PbF2 is left over, but again, it's not going to matter. We have X Pb2 plus, and we have 2X of the F minus. Remember, let's not forget the point of this problem. Our goal is to calculate how much PbF2 dissolves, which is X, and we could actually choose to solve for any X in this ice table, because numerically they're all going to be the same thing. They might have a slightly different sign, but they're all going to be representing the same thing. So in order to solve for X, this is something that you're familiar with. You need to set up an equilibrium expression, KSP. It is your products, Pb2 plus, times the reactant, F minus. Don't forget to square it. Where does that square come from? Comes from the coefficient in the formula. What is our KSP value? It is 4.1 times 10 to the minus 8. And that is X times 2X, which is squared. So the X, which represents the lead ion, and the 2X, which represents the fluoride ion, and don't forget to square it because of the stoichiometry. So let's work the math out on this. 4.1 times 10 to the minus 8 is going to be 4x cubed. Just doing the right side of the equation all together. And let me get my calculator out here. .1 times 10 to the minus 8 divided by 4, and then take the cube root. And it looks like I am getting X is 0.00217. Let's think about what the units are on that X. The ice table default unit, unless we change something, ice table's units are always in molarity. So our X is going to come out with units of molarity or units of moles per liter, which is the units of molar solubility, which is exactly what we're trying to figure out. So this problem is solved. And this is our answer. This is the number of moles per liter of lead fluoride that will dissolve.